All right, welcome. In this video, I'm going to be working Algebra 2 Homework 6.3, which is all about, analyzing graphs, figuring out where they're increasing, decreasing, where they've got maxima and minima. So I think first to start, I'm going to remind you of those kind of four things we talked about. All right, so we're going to say that a function is increasing when, as we move left to right, the graph is going up. So as x increases, the y coordinate on the graph also increases. Decreasing will be, as we move left to right, the graph's going down. Y decreases as x increases. And then a maximum and a minimum, we're going to characterize those as places where the graph switches from increasing to decreasing, or from decreasing to increasing. So for the first problem, it's talking about, here's the graph of a third-degree polynomial. So this is the graph of f of x. And on what intervals is f increasing? I guess it said third degree, so we know that there's not it's not going to turn back around or anything outside of our field of view. So on what intervals is f increasing? It looks, I can see it increasing over here. Definitely looks like an increasing situation when x is bigger than 4. But also over here, I'd say the only way you can go wrong on these types of problems where you're looking at the graph and trying to figure where it's increasing or decreasing is if you kind of get your perspective all off and it's like, oh, I feel like I'm starting from the top and moving left and it's going down, so that feels like decreasing, but we're not moving to the left. We move left to right, just like we write. So I'm going to say, all right, as I move left to right, it's going up here. So this is where x is less than 2 is that maximum spot. So when x is less than positive 2. And then on what intervals is f decreasing? Somewhere where it's going down is really only this middle portion, and that's between 2 and 4. Then what values of x satisfy the inequality f of x is greater than or equal to 0? This is something a little different for us. I didn't really do this in the notes. Just figured I'd go in homework, see how you did on it. All right, so f of x is greater than or equal to 0. In this class, we've seen many times f of x is just a fancy word for the y coordinate on the graph, right? So I want to know where y is greater than or equal to 0. Well, y is equal to 0 here, right, and on the x-axis. And for the graph to have a greater y coordinate than 0 would be just like all of this stuff up here, anywhere we're in the upper half. So that starts when x is 1. Since it's greater than or equal to 0, this is okay that it goes back and it's temporarily equal to 0. So I'm going to say that this is true when x is greater than or equal to 1. That was something a little different. What x values does f have a relative maximum or a relative minimum? Well, I've got them labeled here, so I've got x equals 2 and x equals 4. So x equals 2 is a relative maximum because the graph goes from increasing to decreasing. And then x equals 4 is going to be a relative minimum because the graph goes from decreasing to increasing. And then we're going to write an equation for f of x. So that's like the old thing that we had done, a few times ago, where we're going to look at the factors and the y-intercept and try to, piece something together. And this just says an equation, so I'm not going to write it necessarily in standard form. So I'm going to start with the zeros. I've got a single root at x equals 1 and a double root at x equals 4. So a single root at x equals 1, well, that just means I have x minus 1 as a factor of my polynomial. A double root at x equals 4, that's going to be x minus 4 to the second power. And, well, we want an equation, so it's going to be like y equals, but there could be some leading coefficient, right? Because I need to make sure that whatever I have is going to cause me to run into this point. Maybe I'll just kind of label this. So this is the y-intercept. This is the point where x is 0 and y is negative 2. So in order to solve for a, I'm going to plug in x equals 0 and y equals negative 2. So negative 2 equals a times 0 minus 1 times 0 minus 4 squared. I'm just going to plug in x equals 0, set y equal to negative 2, and solve for a. So if I square negative 4, I'm going to get positive 16. And so I'll have, actually just collect over here, a times negative 16. So I could divide and say a is negative 2 divided by negative 16. That's an eighth. And I feel like I had something else to say about this. Oh, yeah. It's not surprising that I'd see this as 1/8. Okay, it's a positive number, and this is a third-degree polynomial with a positive leading coefficient because of the end behaviors. All right. Next, we're going to consider a function that's given to us algebraically, like that. They just give us a formula. So we're going to start by giving a sketch. We can definitely do that. So I think in order to give a sketch, I'm going to want to know what the zeros are, so I'm going to factor this thing. So I think to myself, and I don't really like it where the leading coefficient is negative, so I'm going to factor out that negative as well. I see 2 powers of x common, so I'm going to say g of x is negative x squared multiplied by x and a minus 2. And that'll make it easier for us to graph. Okay, this is a third-degree polynomial with a negative leading coefficient. So that means that the end behavior is going to look kind of like y equals negative x to the 3. It's going to come from above and then go down eventually. So now I think about my zeros. That's at x equals 0, which is a double root, and x equals 2, which is a single root. Not 4, that's definitely 2. I can fix that. And so I'm going to go in here and kind of write myself an x-axis and label it with 0 and 2. And so if this, if this is the end behavior, the graph is going to come from above. It's going to bounce at x equals 0 because it's a double root. And then it's going to pass through here confidently. So if it's bouncing, it's got to go from positive to 0 back to positive. And then we're going to do a little bit of that. That'll be great. Okay, so that's going to be the sketch of the graph. If you needed a y-axis, which I feel like I've been pretty bad about lately, you could draw it in right there. That would be perfectly fine. Okay, that's the sketch. At what x value does g have a local minimum? Oh, okay, that's going to be x equals 0. Because at least locally, near x equals 0, I'm seeing the graph is looking like that. Right there. Oh, you can't see that, but I just hit that. All right, the graph of g has a local maximum at x equals 1.3. For what x values is g decreasing? Oh, I like that. Okay, so we're going to say that that is 1.3. Okay, decreasing is where as I move left to right, the graph is going down. Y is getting smaller. So I'm feeling like that's going to be happening over here, and then over here as well. So this is where x is less than 0. Or also where x is greater than 1.3. I don't know why I stopped there, because it's going to continue to decrease after it goes negative, right? So x is greater than 0, but also, or no, x is less than 0, also x is greater than 1.3. Okay, and that's going to be where g is decreasing. All right, now we're going to let h of x be half of x plus 1 times x minus 1 squared times x minus 3. What is the degree of h? Okay, that's a good one. I asked that question a lot in my class today, but that's something I'm going to keep harping on you about, because that's really important. Determine, being able to look at a polynomial in a variety of forms and determine the degree and the leading coefficient. All right, so what is the degree of h? Okay, well, it's the highest power of x that I would see if it was written out in standard form. I know what would happen is I've got 1 power here, 2 powers here, so it's a total of 3 powers, and an extra one. That's a degree 4 polynomial. And then what's the leading coefficient of h? Okay, I'm not going to multiply these all out, but I know that if I did just these 3 things in parentheses, I would have x to the 4th and some other stuff. If you think about it, right? If you multiply x times x here, I get 1x squared. I multiply this x by itself when I go to square this thing, and be another x squared, and I multiply those 2 things together, I'm going to get 1x to the 4th. So I know that the leading coefficient has to be this 1/2. okay, which I'm going to point out 1/2 is not as important as the fact that it is a positive number. Okay? So it's a 4th degree polynomial, positive leading coefficient. That means that the end behavior is going to be, more or less like y equals positive x squared. Okay. And then sketch the graph of h, we can definitely do that. Degree 4, positive leading coefficient, zeros at x equals -1, +1, and +3. Okay, so -1, +1, and +3. And what was I going to say about that? Oh, okay, and then this one's going to be, it's going to be a double root here at x equals 1 because of that double exponent there. All right, so I'm going to say, all right, end behavior is this, so that means it comes from above. X equals -1 is a single root, because no higher multiplicity. So we're going to just pass through there with confidence. X equals +1 is a double root, so that's going to bounce. And x equals 3 is a single root, so it's going to go like that. This is not the best sketch. It definitely doesn't. Oh, actually, maybe it does. I don't know. If you want to know what this thing really looks like with the most accurate kind of sketch, you're going to use technology, right? That's going to be really the only way to go. So is h increasing or decreasing at x equals -1? Okay. Well, another way that you can do this, besides just thinking as I move left to right is the function going up and down, is you can look really closely. See, how far does this let me zoom in? Not far enough to then make this thing look like a line. But for smooth functions, you can zoom in far enough and it will appear linear. And if this was a line, it would have negative slope. Okay, and since that line would have negative slope, we'd say the function's decreasing. Pardon me. Hopefully that seems to be the level of zoom I was using before. Okay, so decreasing at x equals -1. And I mean, I'm probably not going to ask you this on the quiz and test, but if you were asked to give a reason for your answer, I think the best answer would be because h goes from positive to 0 to negative. And that's positive to 0 to negative, that's decreasing. All right, and where does h have a local maximum? Okay, that's at x equals 1. And if I had to give a reason for that, I'd go back to the definition of of maximum and minimum, and I'd say because h goes from increasing to decreasing. Does h have a maximum, a minimum, or neither at x equals +3? Nice, good question. Okay, this one's going to be neither because it's continuing to increase through there. I think my reason would be that x equals 3 is not a double root. It's a single root, so it's got to have a sign change. Okay, we know that at a single root of a polynomial, there's always going to be at any odd root, there's going to be a sign change, and with this single root, it's just going to pass through confidently. So does h has neither. X minus 3 is not a double root, or because it is a single root. Okay, where does h have a local minimum? Well, it's got 2 of them, and we don't really have the tools to determine where that's going to be. I think it's in the next unit. We're going to pull out a graphing calculator, and that will really help us figure out what the locations of those are, because there's just like a command that you can do to the calculator. It's like, hey, find me this point right here, the lowest point. I'm going to say it's got 2 local minima, somewhere. It's got one between -1 and 1. But to be more precise than that, we would need to know about calculus. And that's why you're in this algebra class. Maybe one day you're going to calculus, and so I'm not going to ask you to solve that for me right now. That'll be beyond the scope of this course. And then the other one, I would say, is somewhere between x equals 1 and x equals 3. And then, okay, the last problem here, or the last set of problems is, hey, here's a third-degree polynomial. I'm just going to pretty quickly go through these. Relative maximum at x equals 5. Relative minimum at x equals 1. Increasing only here where it's got a positive slope, or where as I move left to right, the graph is going up. That's from x equals 1 to x equals 5. P is decreasing when x is less than positive 1. Right? So move left to right, it's going down here and also going down there. So x is less than 1. Also, x is greater than 5. And, okay, for what values of x is p greater than 0? All right, p, again, represents the y-coordinates, like f of x. Okay, so p is greater than 0. We're looking for where this graph has a positive y-coordinate. So that would be right through here. But not there, right? Because we want it greater than 0, not greater than or equal to 0. Okay? So in terms of x, for what values of x is p greater than 0? All these x values less than negative 1. Okay? And then determine the leading coefficient of p. Well, we're going to start with kind of like a factored form, and then we're just going to solve for it. But right now, because this is a third-degree polynomial, I can tell that it has a negative leading coefficient because of the end behavior. I need this leading coefficient to come back negative. If I don't get a negative number, I will know that I have done something wrong. So I'm going to kind of put down a skeleton. So I've got a single root, so it's going to be some number times, that's the leading coefficient I'm hoping to solve for, x minus negative 1. And that's a single root because it's passing through confidently. And then over here I've got x minus 5, but that's going to be squared because I'm seeing that bounce. It's a double root. So now at this point, I'm going to go in and I'm going to use this value that they gave me. Yeah, because I don't see any other grid intersection points besides here, there, and here. That's what we would need. Maybe that, but that's not. The copy I got did not print well, so I can't really tell for certain if that's going through -2, 4. I'm going to use the one that I am certain about, which is the y-intercept. Okay. So over here, I'm going to say that's the point 0, -2. So I'm going to let x equal 0 and y equal -2. So that'll give me -2 equals a times 0 plus 1 times 0 minus 5 squared. Okay. Now I'll solve for a, and I'll get a is -2 divided by 25. And I think that's going to be all for this video. I hope this helped, and yeah, really thank you for watching.